Hello everyone, welcome back to Discrete Mathematics with me Adila Krishnadi. We are still talking about graph representation. We discussed adjacency list in the previous video, and now we look at the second representation, namely adjacency matrix. Now we distinguish two the matrix for undirected graphs and directed graphs because they are slightly different. So let's start with undirected graph. Suppose you have undirected graph G with n nodes, phi1 to phi(n). So let's say we have n nodes with phi1 to phi(n). Then adjacency matrix of this graph will be n by n matrix. Now the ijth entry, so the entry at i, jth position is aij, and aij is defined to be if I is equal to j, that is aii, then we are looking at loops. It is the number of loops. So k is the number of loops at phi I should say. Yeah. So here in this case, so twice the number of loop at phi I. That will be aii will be twice the number of loop at phi I. And then aij, where I is not equal to j, then this is k here is the number of edges between phi I and phi j. Yeah. So that's how we define it, right? That means each loop at node phi I adds 2 to the entry of aii, and then each edge between phi I and phi j, where I is different than j, adds 1 to entry of aij and agi. Yeah. Of course, if a graph is actually a simple graph without loops and without parallel edges, then the adjacency matrix will contain only 0 or 1, and its diagonal entries are all 0. And adjacency matrix of undirected graphs are symmetric on the main diagonal, and the sum of the ith row, the row I, and is equal to the sum over the ith column, which is the degree of phi I. So let's look at some examples. So again, this is the same graph that we've seen earlier. So what is the adjacency matrix? We have 4 nodes, so that means we have 4 by 4 matrix. So we have, let's say this is A, this is B, this is C, and this is D, and this is A, this is B, this is C, and this is D. And well, the matrix here, let's see, AA there is a loop in AA, so we put 2 here. There is 2 edges between A and B, so we put 2. 1 edges between A and C, so we put 1, and no edge between A and D, so 0. Between B and A, we have 2 edges, and between B, well, there is no loop at B, so 0 here. Between B and C, there is no edge, and there are 2 edges between B and D, so we put 2 here. And then for C, we have 1 edge between C and A, and then we have no edge between C and B, and then no loop at C, and then 2 edges between C and D. And finally at D, we'll have no edge between D and A, and then 2 edges between D and B, 2 edges between D and C, and then 1 loop at D, so we both put 2 here. So yeah, so if you, this is the degree of A, which is actually 5, 4, 3, and 6. So these are the degree of A, B, C, and D, and so is the number if you sum the column, right? Yeah. So that's adjacency matrix. And you see that this is a symmetric matrix. Yeah. Now how about directed graph? If in directed graph, adjacency matrix is slightly different. because you have outgoing and incoming edges. So if you have a a D graph G with nodes phi1 to phi(n), then adjacency matrix of G, called A here, again is n by n matrix with Aij as the I, jth entry, but Aij is different, is defined differently. So Aij contains the number of edges, yeah, from phi I to phi j, yeah, from phi I to phi j. So that means you look at Aij, you look at an outgoing edge from phi I incoming to phi j. Yeah. Now this, we will see that the sum of the ith row is actually the out degree of phi I, and the sum of ith column will be the in degree of phi I. Of course, the diagonal entry Aii is the number of loops at phi I, and because, well, you could have different number of edges outgoing and incoming to for a node, then adjacency matrix of, sorry, it should be directed graph, yeah, adjacency matrix of directed graphs may not be symmetric. Now, so let's look at this example. What is the adjacency matrix of this graph? So we have 6 nodes, so we have 6 by 6 matrix. A, B, C, D, E, F, and then A, B, C, D, E, F. Right. Now A to A, no, 0. A to B is 1. A to C is 0 and 0 and 0 and 0. Now B to A is 0. B to B is 0. B to C is 0. But B to D is also 0. But B to E is 2 actually. And then B to F is 0. And B to so C to A is 0. C to B is 1. C to C is there is 1, and then C to D is 1, and then C to E is 0, and C to F is 0. D to and then from D to A is 0, D to B is 0, D to C is 1, and then D to D is 0, and D to E is 0, and D to F is 0 as well. Now from E to A there is 1 edge, from E to B, no, E to C 0 edge, E to D there is 1 edge, and E to E there is 1 edge, and then E to F is 0, and then F, all zeros here because there is no outgoing edges. There's no outgoing edge from F. So if you sum them here, yeah, you sum them here, is 1, which is the degree of outgoing degree of A, yeah, whereas here if you sum the column, then you get 1 also the incoming degree of A, right? Or for example in E, the incoming degree of E is 3, yeah, and out degree of 3 is also 3. Let's look at D for example. The incoming in degree of D is 2, which is, you see here, the sum, and but the outgoing is 1. Yeah, so you see that so you see that really the sum of the row sum gives us the outgoing degree, and the column sum gives us the incoming degree, right? So that's adjacency matrix, and then let's stop here, and we'll discuss the final representation in the next video.